When engineers and purchasing professionals request a metal finish, they often begin with a familiar process name. They may ask for zinc plating, powder coating, e-coat, liquid paint, or a heavy protective coating. But the most important question is not, what coating do we normally use? The better question is, what does this surface need to do? Does the component need corrosion protection, electrical conductivity, or electrical insulation? Will it be exposed to moisture, road salt, chemicals, abrasion, ultraviolet light, or high temperatures? Are there threaded holes, grounding points, bearing surfaces, or close tolerance dimensions that cannot be coated? And is the part a simple bracket, a welded assembly, a precision fastener, an electrical bus bar, or a large enclosure? Those questions should drive the finishing decision. In this video, we are going to compare 5 major families of metal finishing: metal plating, fluidized bed powder coating, electrostatic powder coating, e-coating, and liquid paint. We will explain where each process works well, where it has limitations, and what engineers and purchasing teams should consider before releasing a part for production. We will also discuss pretreatment, coating thickness, masking, corrosion testing, hydrogen embrittlement, part design, and the information needed for an accurate quotation. There is no universally superior finish. The goal is to select the finish that best matches the component, its environment, its functional requirements, and its manufacturing economics. Metal finishing is the broad practice of changing a metal surface to improve one or more characteristics. These can include corrosion resistance, appearance, wear resistance, chemical resistance, paint adhesion, electrical conductivity, electrical insulation, friction, and cleanability. Metal plating is one category within metal finishing. In plating, a metallic layer is deposited onto another material. Electroplating uses electrical current to deposit that metallic layer. A coating is a broader term. It may be metallic, organic, polymeric, ceramic, or based on a chemical conversion of the original surface. So zinc plating is a metal finish. Powder coating is also a metal finish, but they are not variations of the same process. They create different surfaces and solve different problems. Before selecting a finish, define where and how the part will operate. A component inside a temperature-controlled data center has a very different exposure profile from a bracket underneath agricultural equipment. A fastener inside an electrical cabinet has different requirements from an enclosure installed outdoors near the coast. A wire basket handled repeatedly has different risks from a decorative panel that is rarely touched. Ask several basic questions. Will the part be used indoors or outdoors? Will it encounter water, humidity, condensation, salt, chemicals, fertilizers, fuels, oils, or cleaning solutions? Will it experience abrasion, impact, bending, or repeated handling? Must part of the surface remain electrically conductive? Does the coating need to provide electrical insulation? And what is the expected service life? These questions are more useful than asking only how many hours a finish can survive in a salt spray test. A laboratory corrosion test can help compare controlled coating systems, but it does not perfectly reproduce every real-world environment. A coastal atmosphere, an agricultural application, an indoor electrical room, and the underside of a vehicle expose coatings to very different conditions. The coating specification should be connected to the actual application. The next consideration is the substrate. In other words, the material beneath the finish. Common substrates include low-carbon steel, high-strength steel, stainless steel, aluminum, copper, brass, cast iron, and galvanized materials. A finish that works well on carbon steel may require different pretreatment on aluminum. A process used on mild steel may create additional risks when used on hardened, high-strength steel. Copper and busbar components may need corrosion protection while preserving conductivity at designated contact points. Aluminum may require conversion coating, anodizing, paint, or a combination of treatments. The base material affects cleaning, adhesion, corrosion behavior, and the possibility of hydrogen embrittlement. This is why the material specification cannot be separated from the coating specification. A drawing that says only zinc plate or powder coat black may not provide enough information to consistently produce the expected result. Let us begin with metal plating. Plating applies a relatively thin metallic deposit to a component. Depending on the metal and process, plating can provide corrosion protection, conductivity, solderability, wear resistance, controlled friction, decorative appearance, or a combination of these properties. Common industrial plating systems include zinc, zinc nickel, nickel, electroless nickel, tin, copper, and other engineered deposits. For steel components, zinc is one of the most familiar. Zinc helps protect steel because it acts as a sacrificial coating. Under appropriate conditions, the zinc corrodes preferentially and helps delay corrosion of the underlying steel. But the phrase zinc plated is not a complete specification. A complete requirement may need to define the standard, coating thickness, supplementary treatment, passivate or sealer, appearance, corrosion requirement, masking, and any hydrogen embrittlement precautions. Two components described simply as zinc plated may deliver very different corrosion performance. Plating is often a strong choice when a component requires a relatively thin and controlled finish. Examples include fasteners, stampings, brackets, electrical hardware, connectors, and other components with dimensional requirements. But plating thickness is not perfectly uniform across every geometry. Edges and projections may receive more deposit. Deep recesses and shielded areas may receive less. Blind holes, welded seams, overlapping surfaces, and complex cavities can affect cleaning, rinsing, plating distribution, and drainage. Racking also matters because the component needs reliable electrical contact during the process. The correct plating system therefore depends on the material, geometry, tolerances, volume, and performance requirements. One important risk associated with processing certain high-strength steel components is hydrogen embrittlement. Hydrogen can be introduced during operations such as acid cleaning, pickling, or electroplating. In susceptible materials, absorbed hydrogen can reduce ductility and contribute to delayed cracking under stress. This is particularly important for high-strength fasteners, springs, hardened parts, and safety-critical components. Not every steel component has the same risk. Material strength, hardness, stress, geometry, cleaning methods, and coating process all matter. Post-process baking may be specified to reduce risk by promoting the release of hydrogen. But baking should not be treated as a universal guarantee. The drawing, material certification, applicable standard, and customer specification should define the required controls. The important point is simple. Do not wait until after quotation or production has started to identify that a component is made from high-strength or hardened steel. Material strength, hardness, and hydrogen embrittlement requirements should be identified during the quoting process. Now let us move to fluidized-bed powder coating. Fluidized-bed powder coating is sometimes confused with conventional electrostatic powder coating. Both use powder, but the application methods and typical results can be very different. In a fluidized bed, air moves upward through a container of powder. The air suspends the powder particles so they behave almost like a liquid. The metal component is normally preheated and then immersed into the powder bed. The powder contacts the hot surface, melts, and flows around the component. Depending on the material and process, additional heating or controlled cooling may follow. The result is generally a relatively heavy and continuous coating. Fluidized bed coating can be useful when a component benefits from a heavy protective film, impact resistance, abrasion resistance, chemical resistance, a smooth surface, or electrical insulation. Applications can include wire forms, baskets, racks, guards, handles, clamps, hooks, trays, and selected electrical or material handling components. But fluidized bed coating is not right for every part. The heavy film that makes the process attractive can also create design challenges. A thick coating can interfere with threads, holes, slots, bearing surfaces, grounding points, electrical contacts, and mating assemblies. Complex parts may trap air during immersion. Closely spaced surfaces may bridge. Different thermal masses within the same part can also create thickness variation, and parts that cannot tolerate the required preheating may not be good candidates. Fluidized bed coating should therefore be treated as an engineered process, not simply selected because a heavier coating sounds more durable. Now let us compare fluidized bed coating with conventional electrostatic powder coating. In electrostatic powder coating, Powder particles are charged and sprayed toward a grounded metal component. The powder is attracted to the surface. The part then enters an oven where the coating melts, flows, and cures. The two processes often serve different priorities. Fluidized bed coating commonly emphasizes heavier film build, encapsulation, impact and abrasion resistance, electrical insulation, and protection of wire products or selected complex forms. Electrostatic powder coating commonly emphasizes controlled film thickness, color and gloss selection, decorative appearance, and efficient coating of sheet metal fabrications, cabinets, panels, frames, and welded assemblies. Electrostatic powder generally produces a thinner coating than many fluidized bed thermoplastic systems. That can be an advantage for dimensional control and cosmetic appearance. But electrostatic powder also has limitations. Deep recesses and enclosed geometries can be difficult to coat because of electrostatic effects. Sharp edges may also receive less effective coverage depending on the geometry, powder formulation, application, and cure. So the question is not simply, which coating is tougher? The better question is, which application process, film thickness, material chemistry, and pretreatment system best fit the part? Now let us look at E-coat. E-coat, also called electrophoretic coating or electrodeposition coating, applies paint through an electrically driven immersion process. The component is submerged in a coating bath. Electrical current causes coating material to deposit onto conductive surfaces. Because the component is immersed, E-coat can provide good coverage of complex geometries, including areas that may be difficult to reach with conventional spray application. E-coat is widely used as a corrosion-resistant primer and, in some applications, as the finished coating. Its advantages can include relatively uniform film build, efficient material utilization, corrosion resistance, and suitability for high-volume manufacturing. E-coat is also frequently combined with powder or liquid top coats when additional appearance, ultraviolet stability, chemical resistance, or exterior durability is required. Applications can include transportation components, fabricated brackets and assemblies, appliances, power distribution equipment, and industrial machinery. But immersion does not automatically guarantee perfect coverage. Part cleanliness, pretreatment, drainage, air pockets, electrical contact, rack marks, cure conditions, and geometry still matter. If an area traps air, it may not contact the bath correctly. If a cavity cannot drain, chemistry can become trapped. The part still has to be designed for the finishing process. Now let us look at liquid paint. Liquid paint remains an important choice for industrial components because it offers flexibility in chemistry, color, gloss, texture, repairability, and performance. Liquid systems can include primers, epoxies, polyurethanes, acrylics, high-temperature coatings, chemical-resistant coatings, and specialized military systems such as caulk. Liquid paint can be appropriate when the component is too large or thermally sensitive for conventional powder curing. It can also make sense when specialized chemistry is required, a thin film is needed, multiple coating layers are required, field repair is important, or a customer or military specification requires a particular system. Liquid coating has its own process control requirements. The manufacturer may need to manage mix ratios, pot life, viscosity, atomization, flash time, humidity, film thickness, solvent evaporation, cure temperature, and cure time, and multiple layers must work together. A high-performance top coat cannot compensate for contaminated metal or poor surface preparation. That brings us to one of the most important subjects in the entire finishing process: pretreatment. Regardless of the finish, surface preparation is often the foundation of coating performance. An expensive coating applied over oil, rust, scale, weld contamination, or incompatible pretreatment can fail prematurely. Pretreatment may include cleaning, degreasing, rinsing, acid cleaning, blasting, phosphating, conversion coating, activation, additional rinsing, and controlled drying. The exact sequence depends on the substrate and coating system. Pretreatment removes contamination. It prepares the surface for adhesion, and it can contribute to corrosion resistance. Small problems during pretreatment can create major failures later. Residual oil can cause fissures or loss of adhesion. Rust or scale can remain beneath the coating. Weld contamination can create weak points. Poor rinsing may leave chemical residue. Flash rust can develop before coating, and trapped solutions can later leak from seams and cavities. This is why you should not evaluate a finishing operation only by looking at the paint booth, plating tank, powder gun, or fluidized bed. Cleaning, pretreatment, rinsing, drying, process control, and testing can be just as important as the coating itself. Another important variable is coating thickness. It is tempting to believe that thicker is always better. It is not. A coating that is too thin may not provide the intended corrosion protection, coverage, or wear resistance. But a coating that is too thick can create dimensional interference, thread problems, bridging across holes, cracking, poor appearance, cure problems, additional material cost, and assembly issues. Thickness distribution also matters. A part may meet the average requirement and still have areas that are too thin or too thick. The drawing should define the required thickness range and identify functionally important surfaces. Different processes create different thickness control challenges. In plating, geometry and current density affect deposition. In electrostatic powder, grounding, gun settings, line speed, geometry, and part position matter. In fluidized bed coating, part temperature, immersion time, thermal mass, and coating material influence film build. In liquid painting, viscosity, spray technique, flash time, and the number of coats affect thickness. Thickness should be engineered before production begins. It should not be treated only as a final inspection measurement. Many parts also cannot be coated everywhere. Threads, grounding points, electrical contacts, bearing surfaces, press fits, sealing surfaces, machined interfaces, or assembly holes may need to remain uncoated. That requires masking. Masking may involve plugs, caps, tape, custom fixtures, or other methods. It can appear simple on a drawing, but masking can become a significant finishing cost. Every masked location can require material, application, labor, inspection, removal, and cleanup. And the method needs to remain repeatable at production volume. A plug that works for 10 prototypes may not be economical for 50,000 parts. The coating process also affects the masking solution. Masking that works for liquid paint may not withstand powder coating oven temperatures. A solution used with electrostatic powder may not perform the same way in a fluidized bed process. This is why masking requirements should be discussed during design and quotation, not after production begins. Part design itself can also create or prevent coating problems. Immersion processes require parts to fill and drain properly. Closed tubes, blind cavities, overlapping sheets, and enclosed weldments can trap air or chemistry. Drain and vent holes should be positioned for the actual processing orientation. Rack points should also be considered. Most finishing processes require the component to be held, and some require reliable electrical contact. The rack point may leave a visible mark or locally uncoated area. A good design provides an acceptable location for that contact. Sharp edges also deserve attention. Very sharp edges can receive less effective coating coverage and become potential corrosion weak points. Deburring an appropriate edge radii can improve results. Weld spatter, slag, soot, scale, and poor grinding can also affect appearance and adhesion. Coating will not hide poor preparation, and the coating itself must be included in the dimensional analysis. Threads, slots, holes, and mating features should be evaluated as finished components, not just as bare metal. Now let us talk about corrosion testing. Salt spray testing is frequently used to compare finishes. It can be useful, but it is also frequently misunderstood. Salt spray exposes specimens to a controlled corrosive fog. It may help evaluate process consistency or compare systems under a defined method. However, 500 or 1,000 salt spray hours does not automatically equal a certain number of years in real-world service. Actual environments involve temperature changes, wet and dry cycles, ultraviolet exposure, chemicals, mechanical damage, and other variables. Salt spray also does not tell you everything about adhesion, impact resistance, abrasion, chemical resistance, color retention, or electrical performance. And when someone gives you a salt spray number, ask what failure actually means. Is it white corrosion on the zinc? Red corrosion of the underlying steel? Blistering? Corrosion creep from a scribe? Or loss of adhesion, the substrate, pretreatment, coating thickness, sealer, edge condition, specimen preparation, and test method all affect the result. Do not compare coatings based only on one advertised number. Ask what standard was used. Ask what coating thickness was applied. Ask what constituted failure. And ask whether that failure mode represents the actual application. Let us summarize the major process families. Consider metal plating when you need a relatively thin metallic deposit, sacrificial corrosion protection, conductivity, solderability, wear properties, or another metallic function. It can also be appropriate when dimensional control is important or when the drawing requires a specific plated finish. Consider fluidized-bed coating when you need a heavy, continuous polymer coating with impact, abrasion, chemical, or electrical insulating properties, and the part geometry can accommodate the process and additional thickness. Consider electrostatic powder coating when you need a durable and attractive finish on sheet metal, weldments, cabinets, frames, or industrial assemblies with good control over color, texture, and film thickness. Consider E-coat when you need relatively uniform corrosion-resistant coverage on complex conductive components, particularly as part of a controlled high-volume coating system. And consider liquid paint when you require specialized chemistry, a thin or multi-layer system, field repairability, or compliance with a specific customer or military requirement. These processes are not always mutually exclusive. An E-coated component may receive a powder top coat. A plated component may receive a passivate and sealer. A fabricated assembly may receive pretreatment, primer, and liquid top coat. A component may be coated overall but selectively masked to maintain electrical conductivity at specific locations. Sometimes the right answer is not one coating, it is a coating system. Let us look at 3 practical examples. First, an electrical busbar component. A copper or aluminum busbar may need corrosion protection while maintaining electrical conductivity at bolted connections. A heavy insulating coating over the entire component could interfere with its function. The solution may involve selective plating, conversion coating, another specified metallic deposit, or selective masking. The electrical, thermal, corrosion, and assembly requirements need to be considered together. Second, consider an outdoor fabricated electrical enclosure. This part may face moisture, condensation, ultraviolet exposure, corrosion at edges and welds, handling damage, and long-term cosmetic requirements. A suitable system may include cleaning and pretreatment, followed by E-coat or another primer, and then a durable powder or liquid top coat. The exact selection depends on the specification and operating environment. Third, consider a wire basket, rack, or protective guard. A fluidized-bed thermoplastic coating may provide a heavy, smooth, protective layer. But the design still needs to account for weld quality, preheating, coating buildup, rack points, final dimensions, and areas that must remain uncoated. In all 3 examples, the finish follows the function. The process name should not be the starting point. The component requirement should be the starting point. Now, what does a manufacturer need to quote a finishing project accurately? Whenever possible, provide the current drawing and revision. The base material, material hardness or strength, part dimensions and weight, annual volume and typical release quantity, the required finish, the applicable industry, customer, or engineering standard, required coating thickness, color or gloss requirements, masking locations, hydrogen embrittlement requirements, corrosion testing requirements, other required tests, packaging requirements, and the target production date. Also explain why the project is being quoted. Is it a new design? A resourcing project? A capacity problem? A capacity problem? Or capacity problem? Or a quality problem? That context can reveal manufacturing opportunities that are not obvious from the drawing. Combining fabrication, finishing, assembly, packaging, and shipping under one manufacturing program may reduce transportation, handling, work and process inventory, lead time, and supplier management complexity. At Prince Manufacturing, this is an important part of how we evaluate customer programs. We look at the complete manufacturing value stream, not just the coating operation. Before choosing a finishing supplier, do not ask only, "What is your price?" Ask which processes are performed directly. Ask which processes are supported through qualified partners. Ask what substrates and coating systems they regularly process. Ask about part size and weight limitations. Ask how pretreatment is controlled. Ask how coating thickness is measured. Ask how cure conditions or bath chemistry are monitored. Ask how masking is validated. Ask what testing is performed internally. Ask how traceability and non-conforming material are controlled. And ask how finished components are packaged to prevent damage. The lowest coating price does not always produce the lowest total manufacturing cost. Transportation between multiple suppliers, receiving inspections, packaging, damaged components, queue time, inventory, and schedule variability all contribute to the real cost. A finishing decision should consider the complete value stream. Selecting a metal finish is an engineering decision. It is a manufacturing decision, and it is a supply chain decision. Begin with the operating environment. Identify the likely failure modes. Confirm the base material. Define the functional requirements. Determine where coating is and is not allowed. Account for coating thickness in the design. Specify pretreatment, masking, appearance, testing, and applicable standards. And involve your manufacturing and finishing teams early enough to prevent avoidable problems. Metal plating may be right when the component requires a thin, functional metallic surface. Fluidized bed coating may be appropriate when a heavy protective or insulating polymer layer is needed. Electrostatic powder coating may be ideal for durable and attractive fabricated products. E-coat may provide the corrosion-resistant foundation required by complex components. And liquid paint may provide specialized chemistry, multi-layer protection, repairability, or compliance with a specific requirement. Sometimes the correct answer is a combination of processes. The best finish is not automatically the thickest coating. It is not necessarily the finish with the highest isolated laboratory test number, and it is not the process with the most impressive name. The best finish is the one engineered for the component's actual function and produced through a controlled, repeatable manufacturing system. At Prince Manufacturing, we help customers evaluate more than the coating itself. We can look at the complete program, including metal fabrication, forming, welding, pretreatment, finishing, assembly, packaging, and delivery. With manufacturing operations in the United States and Mexico, Prince can help OEMs evaluate the process, capacity, location, and supply chain structure that best fit their manufacturing program. If you have a component that requires metal plating, fluidized bed coating, powder coating, e-coat, liquid paint, or a combination of manufacturing and finishing processes, contact Prince Manufacturing. Send us your drawing and specifications. Our team can review the application, identify the important technical questions, and help determine the most practical path toward production. Thank you for watching. Prince Manufacturing provides metal manufacturing for data center, power infrastructure, and more. Precision fabrication, coatings, electrical components, and mechanical assemblies for data center, power distribution, and industrial OEMs. Contract manufacturing and nearshoring across the U.S. and Mexico. PrinceManufacturing.com.